When we flip a coin, we are always guaranteed one of two outcomes, either heads or tails. Simple enough, right? In essence, there's only a 50% chance that we'll get either heads or tails. Still, things get a bit more complicated when we want a bigger set of numbers. Say, for example, we wanted to see what the probability is for getting two heads total if we were to flip two coins as one test case. In order to do this, the easiest way is to list all the possible combinations that can occur when we flip two coins. These are two heads, the first flip a head, the second a tail, the first flip a tail, the second a head, and two tails. Since now we know that there is only one case out of these four possible cases for there to be two heads, we know that the probability of this occurring is 25%. Still, seeing is believing, so we went and did 10 sample tests of two flips to get what percentage of the outcomes had two heads. But 6 out of 10 of these sets had two heads, completely different from what we think and has generally been accepted the probability should be. In order to solve this problem, we need a bigger sample size, and the bigger the better. With only 2 coin flips in a test case, bigger sample sizes may seem manageable. But what if we wanted to see the probability of getting 2 heads in a set of 4 coin flips? 5, 10, hundreds, or even thousands? Statisticians have come up with a mathematical formula where the number of ways to get x heads or tails in n number of flips is the number of combinations of n things taken x at a time. This translates into n factorial over x factorial by n minus x factorial. But what is that supposed to mean? I wouldn't be surprised if most of us here understood what this mathematical formula means, but when using large numbers, this formula becomes a headache too. Besides, seeing is believing, right? This is where we can implement the Monte Carlo method. The Monte Carlo method is, in a nutshell, a method that takes a random sample of all variables, which in our case are heads and tails, and runs multiple simulations to calculate an accurate outcome. This could be done physically, of course, but that would mean we would be flipping thousands and thousands of coins, even for a 2-coin set sample. If I were to do 1,000 samples, and each sample took half a minute to both flip the coin and record the result, it would take more than 8 hours total. Luckily for us, we have computers that are way more efficient and faster than us when it comes to doing things like this. Thus, we can code the Monte Carlo method in Python with relatively simple ideas. In order to better explain this to you, we will find the probability of getting at least 2 heads in 4 coin flips. Doing the math, we know this is 68.75%, so we should expect the Monte Carlo method to get close to this. Here's the code for a Monte Carlo method that tests the probability of getting at least 2 heads in 4 coin flips. Let's take it apart. First things first, we need to simulate a coin flip. The first line, import random, imports the random module, which will allow us to randomly pick between 2 choices. Let's move on to the second line, def flip coin. The def part of the line indicates that we, the programmers, are creating a new function, with flip coin being the name of this function. After we have defined this function, the line underneath it, random.choice of list h and t, indicates what the flip coin function will do, which in this case will pick either h for heads or t for tails. Next, we want to define a function that flips a coin as many times as we need it to, and records how many heads and how many tails were in that set. The function we define in this case is called flipCoins, with an s, and within its parentheses is a variable called times. In this case, that means when we call the flipCoins function later on, we'll need to put a number in its parentheses to tell the program how many coin flips are in one sample. This function creates a new list called result, which is empty at first. The line results.append flipCoin runs the flipCoin function, which we previously defined, and returns either h or t. Then, it adds that result from flipCoin to the new result list that was created in the flipCoins function. As it is under for I in range times, this line of code is executed as many times as we originally input for times. This function then returns the new return list, which will consist of h and t. Now, we want to see whether this sample succeeds, as seen in def trial succeeds. So, we create a copy of the list given to us by flipCoins4, which means that there are 4 flips in one sample set, and check using flips.count_h greater or equal to 2 to see whether or not there are at least 2 heads in the sample set, where the function returns true if it does succeed, and false if it doesn't. Finally, we get to odds of at least 2 heads in 4 flips. Trials equals 100. The name is a bit long and could be changed to something shorter, but this name at least gets the idea across. As you can see, the variable within the parentheses of this function, trials, is already predefined to be 100. This means that you can run the function later on without inputting a number in the parentheses, and the variable trials will default to 100. If you were to input a number, however, that inputted number will be saved to the variable trials instead. Here, the function creates a new variable called successes, which is at 0, since we haven't run any samples yet. The line for trial in range trials indicates that the code following it will be run as many times as the number saved to the variable trials. Next comes the conditional. If trial succeeds equals true. This is relatively straightforward, as when this line is executed, it calls the function trial succeeds, which calls all the other previous functions in order to return either true if there are at least 2 heads in the sample set, or false if not. The code then indicates that if trial succeeds returns true, to add 1 to the variable successes. This would mean that for the first time trial succeeds returns true, the variable successes would now have the number 1 saved to it. And if trial succeeds returns true again, then successes would have the number 2 saved to it, etc. The final line of the function returns the variable successes, a number, divided by the variable trials, which is also a number, to return a float or decimal number, most likely less than 1. Now that we've explained and better understood the code, let's try running it with trials of 10. Oh, that's not very close to what we expected it to be. But remember, the fewer trials we have, the less accurate the Monte Carlo method will be. Let's pump up the number of trials to 100. Better, but the computer can handle an even larger number of trials. Let's set the number of trials to 10,000. Yup, that's getting pretty close. And it only took a few seconds for the computer to do this too. This Monte Carlo method shown in the video is relatively simple to create, yet powerful when it comes to testing possible outcomes. If need be, this code could also be adapted to better fit other cases as well. We hope that you have gotten a better understanding of the Monte Carlo method and an appreciation of the power that computers can provide even with some basic knowledge of programming.